Hello, and welcome to this Littelfuse and WATEC webinar. My name is Katie, and I will be your Global Spec moderator. Now I would like to introduce today's presenters. With us today is Jeff Schwartz. Jeff has 28 years of experience developing and supporting electrical and electronic systems for commercial vehicles. Recent concentration has been on BEV, HEV, and FCEV powered commercial vehicles. He is a member of the SAE Truck and Bus Electrical Committee and holds 8 U.S. and global patents. Jeff is the Business Development and Technical Marketing Manager Americas at Littelfuse. Joining Jeff today is Joe Plazik. Joe has been an automotive professional since 2003, moving his way from fleet maintenance management to new product development. For the last 3 years, he has been focused on developing power distribution modules and fuse holders for commercial vehicle applications. Joe is the global manager for the power distribution modules and fuse holders at Littelfuse. Also joining us today to be your Littelfuse WATEC moderator for the question and answer session is Rob Iversrud. Since 2012, Rob has been with WATEC, transitioning from sales account manager to his current role as category and product manager. For the last 3 years, he has been developing a focused approach, engaging key suppliers to maximize potential growth by finding clever solutions to complex problems in a variety of different realms. Gentlemen, I'd like to welcome all of you to today's event, and with that, I'll pass things along to you to get us started. Go right ahead.
What is a PDM? Whether you call it a power distribution module, power distribution unit, power distribution center, electrical center, or an electrical box, it comes down to circuits in an enclosure. The power distribution module distributes power from a central power source to many smaller circuits around the vehicle or equipment. The box directs traffic, switching power and protecting all the circuits from overcurrent and short circuits. It can be used to consolidate devices and wiring and make maintenance and management of the equipment easier. You can reduce very vulnerable connections and wire splices by removing components like diodes, resistors, and capacitors from the wiring harness and placing them in the PDM where they can be protected. As we go forward, it is possible to integrate multiple features into a PDM, such as bus communications, current and voltage sensors, DC to DC converters, and even main battery disconnect, relays, and switches for the reliability and ease of installation and maintenance. What are the different types of PDMs? Configurable PDMs. There are off-the-shelf versions of configurable PDMs, and if you can make this work, it's a really good solution and quick turn because you can buy something off the shelf. As a step up from that, you can actually arrange to have a new label put on a standard off-the-shelf configuration, and you get a customization that allows you to have your circuits, your values, and your name on the PDM. The next step up is to do what's called a board spin, and that's a case where you change the base configuration. You keep the same housing and the plastics, but you change the printed circuit board or change the busing so that you can achieve the custom circuits that you want. And what that allows you to do is essentially have a custom PDM with much smaller required engineering development and fixturing costs. The next type of PDM is a fuse-only PDM. Fuse-only PDMs are bus fuse centers without any relays, usually higher amperage products, usually with bolt-down fuses. They're kind of designed for what we would call as a pre-fuse box. They're placed right between the battery and your main trunk lines, leading out to your main different circuits in the vehicle. Hardwired PDMs are PDMs with limited or no busing. They make connections to devices direct via connection to a terminal on the wiring harness. So in a hardwire box, a terminal from the wiring harness is snapped directly into the back of the box, and that's what makes contact with your devices. Very simple, very robust, very reliable, very flexible. Full custom is the last option, and full custom is, as it says, it can be anything you want it to be. You can include main disconnects. You can include all kinds of things in there. You can shape it so it fits in a difficult position inside the vehicle or application. But It requires a great deal of more of engineering and time. So what are the functions of a PDM? The function of a PDM is to move power around, basically. And how does it do that? There are two main ways that they use to move that around: bus bars and printed circuit board. So printed circuit boards are terrific in terms of their flexibility and the fact that you can basically make them do pretty much anything. You can mount unusual components on them. You don't have to be stuck with a particular style or type of components. But they're limited in terms of the current capacity because the copper is only so thick. When you have a bus bar, it's much thicker and you can carry more current more easily. But you have less flexibility in terms of the routings you can do and in terms of the types and styles of components you do, because the stampings are much more fixed in that sense. So how can I talk to the PDM? Well, again, you can incorporate either CAN or LIN communications into the PDM, and it will talk to your vehicle, to your piece of equipment. And what other things can I add in? Well, you can add in high amperage relays, solid state relays if you want a PWM device. You can also incorporate blown fuse indication to improve maintenance requirements. That can either go over the CAN or LIN bus way it's listed, or it can actually have LED indications of blown fuse. Why do you want a PDM? Number one is reliability. It's a much more reliable setup than discrete wiring with a whole series of small fuse holders. You don't have to have nearly as many connections, and the quality of those connections is usually better. So the wiring point to point also requires you to do multiple test, repair, fix, upgrade, test, repair, fix, upgrade. All those things need to go in multiple cycles. It takes a lot of time. There's a lot of labor in that. The cost of a PDM may be more than the BOM cost of the other, but the labor differential is huge. So also you have a maintenance issue, locating blown fuses, and require many hours of troubleshooting. Centralization, everything is in one box. You know where to find it. So you don't have to go looking for what is a fuse somewhere buried in that harness. And what you can do is you also have a label on there, so you know which fuse is for which circuit, and you know what the proper replacement value is. Also, you have keyed connections, so that all your connections that come into a PDM are keyed, and it's almost impossible to miswire them. So subsystems also arrive tested, so you don't have as much testing. Your wire harness can be tested, your PDM can be tested. You should be able to plug and go with just a quick test. In general, there's less wiring. It's snap-in connectors. It is high current connection, maybe with one connection, but not multiple high current connections to multiple holders. So again, you save on harnessing, you save on mounting positions, you save on hardware, and also because you can put multiple different kinds of components in the box, you don't need to have as many boxes and as many connections. So overall, it's a major system level cost reduction. And I'll turn it over now to Joe.
Thank you, Jeff. So now that we know what a PDM is and what it can do, where does it go? Well, a PDM can go in a multitude different type of applications. As seen on the screen, we would start more commonly with your ground applications. These would be your light, medium duty, and heavy truck and bus, your passenger cars, and your R&Vs. Also, outside of our truck industry, we have our DC power industrial equipment. These are your DC generators, your data hubs, and your distribution robots. Finally, we have construction and ag, and we have marine. Essentially, what I'm saying is PDMs will go in anywhere DC power is present. So now that we know what takes a PDM, what are some of the common mounting locations? One would be our underhood. This would be your firewall or your frame. These are closer to the larger current loads, such as your alternator or starter. Next, your chassis on your frame under the cab. Common on our Class 8 trucks, these are the boxes that would power throughout the cab, moving power from the underhood box. We have our battery box, also found on Class 8 trucks, and an equipment box. These are great for utility vehicles. But now that we know kind of where you can mount them, let's think about what you need to know when mounting them. Common locations in the mounting space in the qualifying conditions, one is your X, Y, and Z space. X, Y, and Z is your height, width, and length of the location you are mounting your PDM. PDMs are a centralized circuit protection box that will need adequate installation and service space. We need to keep our mechanics in mind. So for ease of repair, a good space, accessible space is great and perfect for a PDM. Outside of our wonderful mechanics, we should also keep in mind our harness routings. Our harness routings are going to be ran throughout the vehicle, and that is essentially how we're going to get power through our PDM and to those much needed accessories. We need to ensure that if we are running through a firewall or bulkhead, there's enough room and clearance to get that harness through to your power distribution module. Finally here, when thinking about mounting, we need to think of our environmental considerations. PDMs are built to protect against the environment, but if not all considerations are met, they could be damaged, which would cause damage to your application. Speaking deeper about the environmental specifications, one of the first is IP, ingress protection. Ingress protection is a standard rating that speaks about the protection from solid and liquid immersion into your vehicle, into your PDM. The first digit on the IP chart would denote what's solid, and the second would be liquid. If the PDM is going to be exposed to spray and splash, IP6669K should be the minimum protection you want to think about requiring when you select the PDM. If the possibility exists that the PDM will see continuous exposure or be saturated to spray or splash, we recommend that you would start looking at IP67 and above. Outside of dust and water, one of the additional environmental factors that we need to think about is shock and vibration. Shock and vibration specifications, they provide kind of the overview of the testing criteria to ensure PDMs can operate safely with over-the-road conditions. We follow ISO 16750-3. 16750-3 applies the electric and electronic systems components for road vehicles. This is to ensure that as that truck is traveling down the road, our PDM is not going to vibrate those essential components out or just not work altogether. All right, now that we know where PDMs are mounted and some of the considerations so far, the next should be, what circuits should I consider? PDMs have the heavy lifting job of not only protecting our applications, but controlling and sensing what they are doing during normal operations. When we are selecting a PDM, we should consider some of those common circuits, such as our low voltage mechanical switches that can be used to control accessory lighting, our electromechanical relays, i.e. starter relay, as very important to start our application, high current battery disconnect, our battery master switches, and additionally secondary power distribution modules. Now that we know where PDMs go and what they are, let's think about the deeper internal workings of what a PDM is. Starting with voltage, PDMs have most commonly worked within the 12 to 24 DC range, though not the case anymore as the emerging popularity of EV and XEV, the industry is experiencing voltage ranging up to 1000 volt DC. But though not common, let's think about what we should think about within our working voltages in our application. The voltage rating marked on components indicates that maximum voltage of the circuit for which that component is designed to operate safely. For when selecting or designing our PDM, our components should be equal or voltage rating should exceed the available circuit voltage for the application that that component is being designed into. So what we are saying here is when designing, we need to make sure that we do not exceed the working voltage of our application. Along with voltage, we have amperage or amps. There's a few ways we can consider amps in a PDM. One, we have our normal operating current. This is the rating of a fuse derated to 30% at 25 degrees C. We need to also note that relays do not derate. Additionally, we have the re-rating for higher ambient temperatures. Higher ambient temperatures, as seen in underhood conditions, will cause a fuse to react faster to an overload situations. Also in higher ambient temperatures, relays will start to derate. Along with higher ambient temperatures, we need to consider the inrush current. Inrush is the sudden rush of current, as you see an inrush, the sudden rush of current, which is most commonly seen during startups. And we have our max PDM current rating. Max PDM rated is determined by summing all of the total derated current of all your circuits. When you have these together, these are the amperage considerations when selecting or designing a PDM. And on here, Jeff will tell you how we distribute power.
Let's discuss busing. Busing is how we move electricity around the box. And there are two main methods used for moving this around the box: bus bars and printed circuit boards. Bus bars are big chunks of metal that basically move your power from one area to the other, and they are put together with hardware to transfer power from one bus bar to the next. Advantages: bus bars can carry a lot of current. Bus bars also have some capability to turn prototypes rapidly by doing mechanical type prototypes, but they're not as flexible on routing or as flexible on component type that they can handle. Usually it's very limited because the terminals are essentially stamped as part of the bus bars. Printed circuit boards have traces to make all the connections. Highly flexible. You can put in a lot of different components. You can put in a lot of different types of circuits, but they're power limited because copper is very limited when you put it on the board like that. So you've got to be careful with your copper conservation to make sure that you can move your power around. The best of both worlds is a type of PDM called a hybrid PDM. And the hybrid PDM mixes circuit boards and bus bars, using bus bars to move the higher current and circuit boards to move the control and lower current circuits. It's the most flexible, but almost exclusively it's for custom products. Inputs and outputs. How do I connect stuff to my PDM? How do I connect devices? So the connections in your PDM should allow mechanical and protective devices to be changed. You want to be able to swap them in and out because you're going to get blown fuses. You're going to potentially fail a relay. And the idea is the box should last for the life of the vehicle. Not necessarily all the individual components, but the box should last the life of the vehicle. So they have to be durable enough to stand up to normal vehicle heating and cooling cycles without relaxing the force in the terminals devices. Because if you begin to relax the terminals, you get high resistance and more heating. And the sizing of the terminals and the conductors and current conductors is very important because you have to get sufficient current carrying capability that you're not creating a lot of heat. And communal heating as well can be an issue. Think about it. Fuses are basically resistors. Relay coils generate heat. And also the contacts, when they're carrying a lot of current, generate heat. So there's a lot of heating sources in there. So the connections and the sizing of the wires and the sizing of the terminals is very important to the durability and reliability of your PDM. But the single biggest factor inside of a PDM as to what you're going to do is the space to bus power around, not the space for devices. Usually you can cram more devices in there physically than you can move power around for. Can I fit enough copper in my box to handle my loads? PDMs also supply mechanical support to inserted devices so they can survive the normal vehicle environmental challenges like vibration, heat, and shock. Next, now that I've connected all my devices to my PDM, how do I connect my PDM to the outside world? Terminals and connectors, different types of things. Terminal size is very important. You need to think about what the load is you're carrying, how many amps that terminal can carry. Do I need to split loads? In split load situations, you're actually taking a higher current circuit and splitting it over two smaller terminals, excuse me. Do I have enough I/O to handle all the circuits I want to handle, including my power and including all my high power outputs? Do I want to put a common ground circuit in for all the relays, or a common power circuit for that matter? That would reduce the number of I/Os in, and that helps me use things out. So, do I want a common ground circuit? Control and lower load circuits usually will go through your connectors. And again, you need to make sure you have enough terminals and enough I/O to handle them. High current connections are kind of an interesting situation because they're kind of a key. You've got to get power in, and if you have high current circuits, you've got to get power out. There are three basic ways to do it. Through the connectors. You see that middle connector right there? That one, that middle PDM right there, that one brings all the power in over multiple terminals in the connectors. They just split up the power in and bring it into multiple places. Then you have bolted down connections, such as this one up here, in which you bolted down a large ring terminal directly to the PDM. And the final and most complicated version is what we call keyed snap-in connections. And these are high current connections that snap right in, but have keying in them so that you can't get the connections wrong. And it's also faster in assembly because it's color coded actually in this case. So what type of connectors do I want to use? Custom connections are great because they can be sculpted to get the maximum I/O in the smallest amount of area on a PDM. The problem with custom connections is you've got to do a lot of environmental testing because there's no guarantee that that environmental testing will match with your custom PDM. And the other problem is field replacements. If you ever have to replace that connector, do you have access to the connectors? Can you find them? What's the cost of them also? Because they're obviously lower volume than standard connectors and therefore tend to cost more. Standard connectors obviously are off the shelf. They are easy to get a hold of, and also they've already been tested, so you don't have to do nearly as much environmental testing to prove out the performance of a standard connector. They have existing tooling. However, the problem is when you design around them, you have to build the box around them so that you can accommodate the known and set sizes and get sufficient I/O into that box. What circuit protection can I put in my PDM? Again, remember the rule of circuit protection sizing. For fuses, breakers, and PPTCs, the continuous current should be 70% of the rated load. And what that means is, for instance, if you have a 100 amp load, you should take a 150 amp fuse for that 100 amp load. And that's simple math. You divide the 100 amps by 0.7, it comes up to about 143 amps. The next available size is 150 amps. So a 100 amp load, continuous load, should have a 150 amp fuse. In addition to the continuous current, you should compare the max current and the max current time to the I²T curve on the data sheet to make sure you can handle the fused load. So this is your I²T curve. And let's assume we have our 150 amp fuse, which is the orange line on there, and we put a 200 amp load on it as the max current. As you can see, as long as that 200 amp load lasts for less than about 700 seconds, that fuse will be all right. So you don't need to worry about it, and you've checked your max current and your max current time. Now, what kind of fuses can I use? So, bladed fuses, real easy. They go in, they go out. They're easy to install. They're a little bit harder to get to work correctly with your PDM because they need to have a special type of connector on the board. But they're available, highly available. You can walk into any auto parts store in the country and get them. Mini, ATO, Maxi Plus, Maxi fuses are available. Cartridge fuses are also readily available because they're used heavily in the automotive sector. So you can get either J case, LP J case, low profile J case, or M case available. Now, those are real easy to interface to the PCBA because they just use a blade terminal, and they're medium below for inrush loads. Bolt down fuses, a lot harder to interface to a circuit board or any kind of PDM, simply because you have to find a transition from your bolt down to your PCBA or bus bar. But they're really good for high inrush motor loads or main trunk line loads. Now, circuit breakers and PPTCs, they are resettable devices. Breakers are a thermal device. They heat up. They have a bimetal that breaks the contact when they reach a certain point. Great devices. One problem is they're not as accurate as fuses for their make and break points. Therefore, you need to be a little bit more conservative in selecting a breaker in an application than a fuse. Type 3 breakers. If you're going to use a Type 3 breaker in a PDM, you need to make sure that the cover and the top of the flag on the Type 3 breaker clears the cover. Because if in fact it does not, you can actually get it at a point where you don't get full break if the flag is not allowed to come to full extension. PTCs are positive temperature coefficient devices. And basically what happens is, as they heat up from overcurrent, the resistance goes up, and therefore they begin to stop flow of current through them. They are really good for electronics because there's no make break, and therefore you don't get spikes on them when you get that make and break as you do on a fuse or on a circuit breaker. But they're limited range, relatively low range. Max is probably around 30 amps, whereas circuit breakers can go much higher than that. Also available are diodes and resistors. So you can put diodes and resistors in either ATO or MIDI format directly into your PDM, or if you have a configurable PDM with a circuit board, you can pretty much take any diode or resistor and mount it on the circuit board for incorporation into your electrical system. What relays can I put in a PDM? The most common are your plug-in automotive relays. They go from 12 volts, 70 amps or 80 amps, all the way down to 20 amps, 10 amps at 24 volt. A variety of different sizes. These are all standard sizes as defined by ISO. They go from your power relay to your mini relay to your micro relay, micro 280 relay, and ultra micro 280 relay. In addition to the plug-in relays, also you can have, for instance, a main disconnect relay built into a custom package. It allows you to have one main battery connection to your PDM, and your main disconnect is also integrated in there. How do I make my PDM smart? You can have a number of features on board that make it smart. It's possible to have microprocessor on board. You can have CAN and LIN communications. You can have a microprocessor on board that sequences things, for instance. You can send a single signal to the fuse box or to the PDM, and it will turn on several circuits. It can turn off other circuits simultaneously. The PDM can also make sure that two circuits, for instance, are not activated at the same time. So those things can be built into the box with intelligence with a micro. In addition, you can also add communications, high speed on CAN, lower speed on LIN. You can also incorporate things like voltage and current sensors that will help you manage your batteries and manage your system. So last but not least, checklist. First thing, develop a schematic. Understand your loads, understand your currents for the loads, both the continuous current and your max current, and the duration of that max current, so you can size the fusing correctly. All those things are critical. You need to understand both internal and external standards that you want to follow on wire sizing and on terminal sizing. What do I need to do for my loads to be able to pass my own internal and standard external requirements for those interfaces between my harness and the PDM? What's the voltage of my loads? I need to understand that. Do I require PWM for any of these loads? That's important because then you have to look at potentially incorporated solid state relays into the PDM, and that will drive your PDM in a certain direction. IO planning. Understand what all your inputs and outputs are. Am I going with CAN? Am I going with LIN to control my relays? All those things will drive your IO count, because if you don't go with a bus system, you have to have individual control circuits for all the relay coils. So those things are important. Your IO, your loads, and your voltage, and do I run communications, and what are my external standards to judge my wire sizing and terminal sizing. And I'll turn it over to Joe for the last slide.
Thanks, Jeff. I want to say thank you to everybody for your attention today. Greatly appreciate you watching this presentation on how to select a PDM. One of the things that I wanted to leave you with is the available resources you can use on Littelfuse.com to find what you're looking for through our PDM selection, our data sheets, our PDM brochures, our white papers, our 3D models, and our 2D prints. These are all available. Just go to littelfuse.com/PDM.
Thank you so much for the great presentation, Joe and Jeff. We have some questions that have come in from the attendees, so we're going to move into the answering those right now. Now, first, what are some aspects typically overlooked when designing in a power distribution module?
I'll take that one, Joe. Probably one of the biggest things is the overall current budget for the box. When you start to figure out all your circuits and you begin to add up everything that you're going to try and control, what is the continuous value? What are these things? Sometimes you can be surprised with how much current you're actually handling, and fitting all that in a box that then fits into your available space can be very challenging. So you need to really understand what your total current budget is, how much you're going to use, what kind and type of loads is another thing that gets overlooked. Sometimes you have inductive or motor loads or high resistance lamp type loads, and those will incur higher inrush, and you need to plan for those in your design with your fuse choices, with your wire sizes and terminals to make sure that you have enough capacity. And also the other thing is sizing the fuses correctly, making sure that you understand what your continuous current load and what your inrush loads actually are, so that you can compare them to the ratings of the fuses and how they should be sized. Those are the things that we tend to see have to require more attention as we get them.
Thanks, Jeff. What are the common difficulties encountered with existing systems incorporating secondary or main power distribution modules?
I got this one, Jeff. Good question, Rob. I would say one of the biggest difficulties we have been experiencing or challenges is integrating into a system that has had legacy existing PDMs. Incorporating into our system, one of the overlooked and difficulty sections, as Jeff was explaining in the presentation, is the connectors. The decision between custom and market available connectors. Obviously, when choosing a PDM off the shelf that you're trying to replace on a current application, having those connectors can be difficult. So yes, custom connectors, they serve a purpose and they're there, but I would say connections to the harness to the PDMs are some of the challenges when replacing into the system and should be focused on before selecting a PDM.
Thanks, Joe. Another question, what do you guys see as the biggest challenge facing engineers with increased voltage requirements?
I got that. It's probably the biggest thing is the non-availability of appropriate components. One of the things we're seeing in there is the creation of electric vehicles is far outstripping the ability of the component suppliers to develop qualified products to meet that need. So in many cases, the device you want the fuse you want, the relay you want is out there, but it hasn't been qualified for automotive application. In particular, we're seeing that particularly in high voltage fuses, things like that. In addition, a couple other things that become important, more important than ever when you're dealing with the higher voltages. Number one is sealing. With high voltage, your ability to drive galvanic corrosion is tremendous. So that if you have a higher voltage application and you're using unsealed open terminal connections, either to fuses or to anything, you are tremendously increasing your risk of galvanic corrosion. In addition, the other thing is arcing. Um, Arcing is a really big problem in higher voltage, both fuses and relays. As you get up in those higher ranges, you get much more arcing and much more damage takes place. So you need to make sure the components you're suggesting or thinking about using are truly rated for the higher voltages you want to use.
Thanks, Jeff. That was very insightful. As a reminder, if you have any questions today, please enter it into the Q&A window below and click submit. We will do our best to answer as many questions as possible. If we don't get to your question, we will follow up with you after today's webinar. Another question's coming in. Are there any other components I should also think about when evaluating my power distribution module for a new or existing build?
I got that, Joe. Couple things you should definitely think about. If, for instance, you have resistors or capacitors or diodes that are spaced around your wiring harness and spliced in, those become potential areas of maintenance and failure. If you could think about moving those devices inside the PDM, tremendous benefit for reliability, tremendous benefit for maintenance. They don't become a point that people have to go looking through a long loom looking for a particular component. Also, should think about integrating things like current sensors. If you're already using a current sensor, you can integrate it into the PDM. You don't have to make a separate connection. You can eliminate wires. Some PDMs we can even also integrate in higher current fuses. So you can eliminate another box. You can eliminate another set of wires. All those things, anytime you can integrate more stuff into the PDM, you eliminate wires, you eliminate connections, and you increase your reliability.
Fantastic. What is the difference between hardwired and configurable power distribution modules?
I got this, Jeff. As we saw earlier in the presentation, Jeff gave a good quick overview. Hardwired boxes are great PDMs, limited busing and require direct wiring. Our configurable PDMs, those are I/O masters, as they have an input that is controlled through a busing system like a PCBA. Sometimes they will incorporate multiple types of busing between PCBA and bus bars. So the advantage is being able to fit more I/O into one box with the configurable PDM, as where on the hardwire boxes, which have limited to no busing and direct wiring, it's a lot more single point, one in, one out kind of wire loom that you have to create, as to where you can take a connector and just plug into a PDM, into a configurable PDM.
Thanks, Joe. Am I forced to use just one type of circuit protection device for my electrical requirements? Or can I use different styles like fuses or breakers or relays?
I've got that. It's pretty much, if you have a spot that you can fit it in your PDM, that's really what kind of determines that. I mean, some PDMs are very limited for what you can use. They only, for instance, use 2.8 millimeter terminals. We tend to design in multiple options, different fuses, different relays, also some breakers. We normally figure on being able to accommodate fuses, breakers, or PPTCs in any location that we can handle in a mini device, because all those exist in that. If you're talking about ATO devices, again, we will integrate in the capability of handling circuit breakers in there as well. So Yeah, you can pretty much use anything. If you're going to use a configurable PDM, it may require some additional tooling, um, particularly to handle the mechanical portion of the interface if we don't have an existing mechanical portion that can handle that device. Um, the other thing that might be is it might require a new terminal on the printed circuit board. So there's some tooling, but it's not the equivalent to a complete custom solution.
Thank you. What are some things I must know in advance before I start evaluating a power distribution module for my build?
I got that one, Jeff, and that is a great question. So a few items that we would recommend you would take a look at is, one, how many circuits you want to protect, and two, the max current capability of the system. So not only how many circuits you want to protect, but what is the current that will be moving through your system for those circuits. And those are getting you on the right path. Helping additionally would be knowing your packaging space. Packaging space as in where you're going to place that PDM and the environmental protection that that PDM will need to have prior to you placing it, i.e. if you were going to go on chassis below cab, it would be recommended that you have an IP67 sealed device and be thinking of that voltage rating. So, or not that voltage rating, that ceiling rating. So circuits, the max current of your vehicle and or your application for that, the circuits you are protecting, and the space where you would want to put it.
Thanks, Joe. Where can I go to learn more about topics like this today?
I had that one as well. You are to find out more information about everything you've seen today, including data sheets, 3D images, 2D prints, and product collateral like brochures. You can go to littelfuse.com/PDM.
Thank you. All right, those are all the questions we're going to get to today. I just want to say a special thanks to Jeff Schwartz and Joe Plazik for guiding us with the tools and knowledge needed to make informed decisions on how to choose a power distribution module. Thank you all for participating today and submitting some great questions. Now, Katie, I'll pass things back to you for some closing remarks.
Thank you so much, Rob. As Rob mentioned, we are going to wrap things up right there, and I just have a few remarks before we go. Rob, Jeff, and Joe, thank you so much for taking time to be here with all of us today, and I want to say a huge thank you to our audience members for being part of this webinar event. Take care, and we will speak with you soon.